Welcome everyone to Chicago White Metal's webinar series. For those of you that have logged on and are hearing me, my name is John Miller. I'm delaying just a little bit more as I can see there's still some people that are logging on. But I want to make sure that I use your time effectively. So I will get started and those of you logging on will catch up. Today's webinar, as you can see, is titled High Pressure Die Casting, Is It Right for Your Part? So, introducing myself, this is John Miller. I'm the Vice President of Sales and Marketing for Chicago White Metal, where I've been here for 7 years. But joining me today, I've got team members from Chicago White Metal's engineering team, and that would be Rob Malarkey, Neil Brown, Hank Rumke, and Alex Hine. Together, we're going to work through this webinar and do our best to equip you with what we hope are some useful guidelines so that you're better able to determine where die casting can be the solution to your component needs. Also assisting today is Mike Dimitrov. He's going to be working in the background, assisting to answer any questions that you might have. Mike Dimitrov, our inside sales manager and resident die cast expert, has over 28 years of experience at Chicago White Metal. And so while we're going through the webinar, we will invite you to participate by sending in questions and a little bit about how we do that. So if you look at the bottom right hand of your control panel, you should see a box similar to what's indicated there on the screen. The questions then are typed in kind of like a chat mode. Type your question in, hit enter, and we'll attempt to give you a live answer. If Mike can keep up, he will do that, and if at the same time, if he gets backlogged, we will make sure that all questions will get answered, even if it requires a follow-up email or something after the webinar concludes. So please send in any and all questions as we go through this. To go through a little bit of the history, just to give you a feel, we've been doing this now for a few years. This is the 11th webinar in the series. We typically do 2 to 3 per year. We've covered a broad range of topics. And all of these webinars are still available to you. So if you missed them and like to go back and see those, they are available for viewing. You will need to register on our DC Squared Die Cast Design Center. It's available through our website, and we'll cover how you access that a little bit later in the webinar. But these webinars are stored there, including the one that we're doing today, so you're certainly welcome to take notes, but you'll be able to have access to it later on. So today's webinar, in order to answer that question, high pressure die casting, is it right for your part? I thought it appropriate to first kind of cover the basics of what is die casting. Many of you might be familiar already, and some, and in fact I hope many, are coming to this webinar because you have experience with other processes and materials and would like to know more about die casting. So just to give you sort of a basic overview of die casting, what is it? Die casting, first of all, is a commonly used term, but when we speak of die casting, we're really talking about high pressure die casting. Low pressure die casting is commonly referred to as permanent mold casting. So when we use the word high pressure, we're really speaking of, or when we use the word die casting, we're speaking of high pressure die casting. And it's a process that quickly converts non-ferrous metals from their liquid shape or liquid to solid, especially aluminum, zinc, and magnesium. There are some other alloys, but those are the main three. And this process converts them from liquid to solid and makes nearly a net-shaped part. It's very efficient in doing that. Molten metal is forced under high pressure into a mold. That mold is created using 2 hardened tool steel dies, which have been machined into the specific shape and geometry of the part. And the process works similar in that respect to an injection molding process. The dies are mounted to a machine that holds the dies shut and absorbs the force as molten metal is injected under tremendous pressure. The process can utilize either a hot or a cold chamber machine as part of its casting process, and we'll describe a little bit more about that later. Die casting, compared to other casting processes, involves significant capital cost and tooling expense, but its cycle times can be a few seconds to maybe a couple of minutes, which is why die casting produces more castings at lower cost than any other casting process. It's really the most efficient way in one process to go from raw material metal to a net shape part. It's also characterized by very good surface finish, at least according to casting standards, and compared to other casting processes, exceptional dimensional accuracy. So a little bit about those two processes that I mentioned. Cold chamber is called that because the components of the machine reside outside of the metal. So cold chamber, and I'm triggering the animation now so you can see that, involves liquid molten metal poured into a horizontal shot sleeve, and that's really sitting in air. It's part of the machine, but surrounded by air. And as the molten metal is poured in, the plunger pushes it forward into the die. The die holds it there until it solidifies, and then the die opens and the part is ejected off. The hot chamber process, shown on the right there, very similar. The difference being that the componentry, some of the componentry, is submerged inside the molten metal bath. Hence, that's why it's called hot chamber. So you would see cold chamber processes used for aluminum always, whereas for hot chamber, it's always used for zinc, or I should say, other than a few rare zinc alloys. Magnesium, being a metal that has less affinity for die steel or other steel components, and less BTUs than what's given up in aluminum, it's able to be cast in either process. So you will see die casters casting magnesium both. We have cold chamber and hot chamber machine technology. So again, the animation is showing molten metal pushed into the die, which is mounted into a machine, held in place for the solidification process, which could be just a few seconds to a couple of minutes, opened up and ejected. So very quickly converting raw material to nearly a net shape part. So with that kind of background, now to talk a little bit more about the focus of this webinar. Where does it make sense to use high pressure die casting? Is it right for your part? And I want to just kind of give you a feel of how we answer that question when we're asked to consider to make a certain application. And giving you, I'm hoping to give you some of those guidelines so that you can begin to make some of these decisions yourself. But there's a number of qualification factors that have to be looked into before determining the answer. These are some of the factors here. What is the annual and lifetime quantity? We'll talk more about the fact that die casting is generally reserved for higher volume, or at least it's a very good fit if it's high volume. But sometimes low volume on an annual basis, but a situation where the application is known to last many, many years would justify the tooling. What are the material property requirements of the application? You know, what kind of environment is it in? Is it need to be stiff? Does it need to be strong? Does it need to withstand chemical attack? Those are some of the things that we would need to know. What is its general part size? What are some of the features, the tolerances that are required, and so on? What are the blueprint notes and the requirements? The geometry itself. Some geometries cannot be die cast, or could be die cast but are simple enough that could probably be more effectively made some other way, which is really the next bullet point. And I hope you'll see as we go through this, we're going to take an approach that says die casting is not an appropriate process for every part, obviously. So certainly we're going to talk about where it could be more effectively made with another process. And then the cosmetic requirements, which I have to admit sometimes are sort of left for discussion later and maybe should have been discussed up front. because it's best to sort of take in all of these considerations or qualification factors up front and all at the same time. Finally, the performance in the environment. You know, is it cycling with thermals? Is it exposed to atmosphere? Is it under a lot of force, or is there a fatigue factor? These are all factors to consider. And so in order to understand all those factors, we have to ask a lot of questions. And admittedly, it might seem as if we're asking too many questions when presented with an opportunity to quote a project. But the more we know about the application, the better. So we're really looking to try to understand not just the component itself, which might be conveyed in the form of a CAD model and a print, but we want to understand what the application is. How is it used? What are its functional requirements, its cosmetic requirements? What are the key features, especially if it's being converted from another process? The design might be what it is based on constraints of the previous process. And it would be difficult without us asking the right questions. It would be difficult for us to understand what features in that geometry are really critical and what are there because they were sort of migrated over from a previous process. And we'll look to understand the entire assembly, you know, what mounts to it and how those other components relate to it. Sometimes understanding the whole assembly can lead to opportunities where we can combine parts and make more of a system piece instead of a single component. And again, as we'll look into this situation, we'll need to understand if there really is a better way to make it. And if so, we'll certainly tell you. So covering these a little bit in more detail now. Volume, annual and lifetime quantity. Low volume is not necessarily a showstopper. I would say, general rule of thumb, you don't typically see die casting work for parts that have less than 2,500 pieces a year, but at the same time I could name numerous applications where it does work. In fact, Chicago White Metal casts a number of applications where the volumes might be only 500 a year. So volume is certainly a qualification factor, but it's not the end all. There needs to be enough volume to justify what essentially is higher tooling costs for high pressure die casting than for other casting processes. And one thing that has to be factored in is if the die casting process itself can almost give you the complete knit shaped part, then it ends up being very effective. If, though, it requires still considerable amount of additional finishing work, such as machining and coating and buffing and polishing, then perhaps there might be other ways to make it work more effectively. So these are some of the factors. In order to understand, though, what makes a good die casting, it's also helpful for you to understand the general economics of the process. So I've broken up economics into really 4 categories. First is the initial investment. It's been alluded to, the tooling cost is higher than on competing processes, at least other casting processes. And that initial investment can be affected considerably by the complexity, whether there are side actions in the tool or if it's simply open and shut, the complexity of the features in general, the type of tooling. Tooling can be single cavity, making one part per shot or per cycle, or it can be multi-cavity, or it can be a family tool where you're making part A and part B in the same shot, and so on. And the amount of engineering, the sampling cost, initial sampling of the die, the prove out of the process, the first article inspection, the production part approval process requirements, those I would consider to all be part of the initial investment or tooling cost. Then there's the per piece, or what goes into the casting cost. And so really there are 3 groups. It just starts on the lower left, finishes up on the upper right. But per piece costs on a casting basis consist of labor, metal, the machine cost, and machine costs vary with the size of the machine, the type of the machine, and so on. Obviously the cycle time drives all of that. A number of cavities, whether it's automated or requires additional labor. Then there's the per piece costs that have to do with post-casting, deburring, sanding, buffing, machining, surface treatments, assemblies, all these are part of the post-casting costs that make up per piece price. And then finally, there are costs that are really more of a per order cost. And those are typically allocated to the piece cost. So you may not see them, but I think it's important for you to understand that from a die caster's perspective, there's a setup of the tool, and there's the preheating of that tool once it's in the machine before you're ready to run production. But along with that, there's a lot of setup-related costs. The tool needs to be prepped. Typically, it goes through a tool room prep where a number of checks are given to the tooling, PM is done, and so on. There's a number of qualification steps. When the first piece is made, it typically goes to the lab for a real scrutiny to make sure that it's approved before production starts. There's obviously the scheduling, the billing that goes into the order. I've already mentioned tool PM. There's a number of documentation. Obviously, there's certs of compliance and other check sheets and so on that are filled out. So these drive some of the per order cost. And like I said, they're typically allocated to a piece price, but that would explain why it's typical to see a per piece price being considerably higher on a low volume order of, let's say, 500 pieces versus a much higher volume order of like 10,000 pieces, where the per order costs become very, very small at that point. One of those drivers that I mentioned, material cost, just to give you a little feel for that. Die casting by itself is a very material efficient process. Excess material that comes from the process is all completely recyclable, and oftentimes the yield, and by yield I mean the part weight as a percentage of the total shot weight, it could be more than 70%, where maybe 50% is typical, but certainly there are some parts with much higher yields. So it's very efficient, but still material cost is a driver. It has to compete with other materials and processes, such as sheet metal, injection molded plastics, etc. And it would be a very complex chart to try to show you material costs compared to everything else. But looking strictly at the three main families of die casting alloys, you can see that generally aluminum is a lower cost per pound. Market prices right now at 82 cents, but it's also a lower cost per unit of volume. I put a cost in here of 8 cents per cubic inch. The zinc price is $1.24 a pound currently. Translating that, it's a heavier material. It's 30 cents per cubic inch. And magnesium, though it's the highest price per pound, it's also the least dense material. And so when you translate that into a unit of volume, it's not far from aluminum, and it is much less than zinc. So magnesium sometimes gets a bad rap because of its higher price per pound, but it is really sold when you put it into a part on a per volume basis. Material requirements: strength, weight, thermal conductivity, electrical conductivity, cosmetic appearance, corrosion resistance. These are all factors that have to be considered. Some of those factors will drive geometry. Some of the factors will drive additional finishing that's required, coatings and so on. And so comparing the three primary alloys, one of each family, the most common aluminum alloy is A380, the most common magnesium is AC91D, and the most common zinc is zinc number 3, or sometimes called Zamac 3. So just putting together a chart where the number 1 would be best, 3 would be worst, trying to give you a sense of how these materials compare. So zinc from a yield strength is very effective, but obviously it's higher weight. A strength to weight ratio is the least effective, whereas magnesium claims the number 1 position in that category. Magnesium also is very energy absorption. It's got a very good energy absorption, I should say. Thermal conductivity, zinc, though aluminum, magnesium also do a very good job of that. Surface quality, there certainly is a lot of applications where zinc is chrome plated and so on. It has excellent surface quality. Corrosion resistance also is good for zinc, not as good for aluminum. Magnesium is in the middle, though I do have an asterisk by it because magnesium in plain atmospheric corrosion tests slightly outperforms aluminum. It's pretty close, but it does suffer from a potential galvanic corrosion. So that has to be considered, and again, that's why we would need to ask questions about what it's mounted to, what is the atmosphere that it's in, and so on. Density, magnesium is the least of weight and zinc the heaviest. Draft analysis, you can see how that breaks down, zinc being preferred. Being able to cast in walls also is best for zinc. So, you look through these and you see a lot of number ones for zinc or magnesium, not so many for aluminum until you get down to the bottom, whereas material cost is generally best with aluminum. And it's not true, of course, for every application, but cost is probably a bigger driver than many of these other factors, and so that's why aluminum still leads the way in terms of die casting. By far, there are more aluminum die castings than any other material. So with that, I'm going to turn it over to one of my colleagues. So Rob Malarkey, Assistant Director of Engineering, is going to present next.
Hi, everyone. So at this point, we've kind of gone through what are the differences in between the metals. What we're going to talk about in this next section is what are some generalities that you can use when talking about designing a new product or converting a current product. We can really only speak in generalities without actually looking through a specific part, but we can help guide you through webinars like this, or if there's a more specific instance where you want to provide us a model and a print to ask our thoughts on a conversion or a new product, we're happy to help. So, but just to kind of go through some of the things that you would be thinking about. Wall thicknesses, it's an important process in die casting to have as consistent a wall thickness as possible. When you have thicker sections or thinner sections than what the nominal values are throughout the rest of the part, that can tend to lead to defects that may or may not be acceptable. Each one of the parts that we receive that we get a PO for and eventually tool up, we'll go through a full simulation process where we'll take a look at what are some of the potential issues. But before we even get to that point, we use common sense to help guide you through wall thicknesses, draft, so making sure that you have enough of an angle on vertical walls to release properly from the tool. Undercuts, something that could potentially be done with other casting processes, but in general is not a common use in die casting applications. Parting line placement, we can talk about what gate and vestige remnants you'll see on the parting line, also where to advantageously place your parting line so you can get the best fill possible and allow air to escape the part as efficiently as possible. And just the general complexity of the part. Sometimes it makes sense from a die casting application that you say, okay, I can fit these 3 pieces all into one piece. We cast away, and I've reduced the number of SKUs that I have for an assembly. But we may recommend, if the one-piece application comes across the quote desk and we see that it needs 4 slides, we may end up splitting that into 2 parts. And we can help you with that process, and it'll make for a more efficient assembly, we often see, and just a lower total cost if you want to look at it that way. So the wall thickness thing that was in the previous slide, this just kind of shows some techniques that you can think about doing when you're either doing a conversion or a completely new design. In the die casting world, a thicker wall section does not necessarily mean that you're going to get a higher strength value out of it. What you'll see in the next slide as well is that the use of ribs and really well thought out metal savers can actually increase the strength of your part without actually adding mass to it. The strongest section of a die casting is within the first 20 thou or so of the outer wall. It's what we call the skin of the die casting. And then as you go inwards, the material properties tend to be weaker. So if we can get a good consistent wall thickness for the given material and do some smart coring out of the thicker sections, you usually end up with a pretty strong part. These are some of the ribs that I talked about in the previous slide. So in the top left corners, you can see where if you have a slightly smaller rib than the nominal wall thickness, generally that doesn't cause too many problems. But the one to the right, well, it's the top middle view where the H value is much greater than the T value. That would be a time where you'd want to core out underneath where that rib is standing out. Similarly, what's really telling is in the bottom views, you've got the one on the left that says generous draft and fillets, angular transition. That's the mark of a well-designed, well-thought-out casting where we're getting no sharp corners. Sharp corners tend to increase the thermal fatigue on the steel and make dies not last quite as long as they should. And then the one on the right also shows where sharp corners, small radii, little draft. That would be indicative of an area where we'd start to see what we call heat check. which is the steel actually breaking down sooner than we'd like it to. Dies can't last forever, unfortunately, but if you're smart about how you design a product up front, we can make them last as long as possible. So this slide here shows kind of what the results of a thick section can be. The middle line right there is showing what is basically the last part of that wall thickness to fill. So in some of these outside corners right here, you can see this is actually surrounded by colder steel. So this corner is actually going to cool faster than this inside corner. And then similarly in this section right here, where we have a thicker section, die castings will freeze from this outer wall and then pull material from the inside and freeze from the outside in terms of the actual part. So this center section, if we leave this thick, if we don't core this out, it's vulnerable to what we call shrinkage porosity. And the less shrinkage porosity we have, the more consistent material properties you'll get out of your die casting, and just leads to a better part.
Okay, next Alex Hine is going to take control of the presentation.
Hi, so as Robin mentioned earlier, one of the notes we want to keep a careful eye on are the draft requirements on the parts. As it says, highly desirable to have draft on all surfaces parallel to the draw of the two dies. Or in other words, all these surfaces that are perpendicular to the parting line should have draft on them. NADCA, the North American Die Casting Association standards, does do a very good job of highlighting the areas that should have draft and what kind of factor that should take part in your part design. It is very part dependent. Some geometry, depending on how deep a boss or cored hole is, should have different degrees of draft on it, whether it should be a high degree or low degree. In some special cases, depending on the part size and where it's located, some areas can have the draft eliminated completely. But as a general rule of thumb, it is recommended that all inside surfaces have about 2 times the draft that outside surfaces of the part does. Here are just 3 examples of undercuts, or some 3 pictures that show a good representation of undercuts that are sometimes found in initial part geometries. As kind of shown on the far left picture, there are no undercuts. Everything is drafted really well from the parting line. The middle image, you can see on the top portion, there are 2 kind of hooks, and as the part would try to eject off the 1/2 of the die, they would grab on and hold onto the die, so you wouldn't be able to functionally eject it. Maybe it would get stuck, or they would completely break off. The third image on the far right, you'd be able to draft appropriately the top section of it. However, because there's that gap between the casting and the parting line, you would not be able to form that feature. The only way that would work is if you somehow wanted to jog up the parting line either between the 2 core dot areas or that kind of situation. You have to adjust the parting line in some variation to make that work. So here's just an example of what a parting line would end up looking like on a part itself. This one's pretty simplified, with just being halfway across. The parting line will be present on all die-cast parts. However, if you're using good part geometry, you're able to either eliminate it completely by moving the parting line to an edge of the casting, so it will not actually appear on it. Or if it is going to be directly in the middle, there are some post-processing that can be done to eliminate the appearance of that parting line, like sanding, vibing, that kind of situation. So there are ways around having that being on the casting.
Thanks, Alex. Hank Rumpke is going to talk about cosmetic requirements.
So up to this point, we've talked about aspects of a part that will help make it as far as out of the die-cast die and die-cast production itself. But now we're looking more towards the finishing part of your product. And whether it is a brand new product or an existing product that you're looking to change processes in order to make it, you generally have the idea of what your part needs to look like in its final function. But it may not necessarily come out that way just from die casting. Now, die casting can produce very surface finishes on parts. Some geometries of parts aren't conducive to it, so certain types of finishes may be needed. Also, there could be finishes required in order for functionality. They're masking or buffing or whatever they may be. So to go over the different types of treatments, you have mechanical finishes such as vibratory diverting, which you put parts in a tank with small or medium to smooth out the surface, sanding, buffing. If you need a nice smooth surface finish for just a cosmetic part. There's also chemical finishing, acid etching for magnesium, aluminum, all types of metals for adhesive purposes, anodizing for strength purposes, coatings, whether that be functional or cosmetic, e-coat for more parts used in the medical field or others, painting, grayish, whitish, depending on the type of metal you're using, may not look best to your end customer, so you may need to paint it. For parts used in pressurized environments, it is often recommended to have the parts impreg. Helps fill out the casting if there's any slight porosity or other things. And then pad printing and silk screening if you need text on your parts. That is also another option. Masking, a lot can go into this, big cost driver. Different parts will have to be blocked off so paint or any type of surface treatment doesn't go on it. Sometimes it's better to just machine it off and could save you money. But if you just rather have the exposed metal without it being machined, you may need to do it, but it is a big cost driver. You might want to look into the part design itself to try and avoid these costs, then don't even have to go down that road to begin with. Another thing to notice or take note of when designing a part, especially if it's going to be e-coated or anodized, is to take note of racking. There are rack marks or slight burn marks that may appear on your part because of the nature of the process. So if it would be beneficial for cosmetic requirements, you might want to look into modifying certain geometries so that it's not as visible on the end product. And now I'll hand it over to Neil Brown.
Thank you, Hank. Okay, so far we've talked about things to consider when designing the actual part. And now I'm going to transition into things to think about when designing your blueprint and the notes for your part. I would say first and foremost, the most important thing is upfront communication with your die casting source while the part is being designed. A lot of the times the part will go through all these modifications to make it a die castable part, and we forget about the blueprint, and then it throws a curveball at the last second that can just cause a lot of issues with delays or add surprise costs or things like that. So I'm going to talk about things to consider both for dimensional specifications and cosmetic or functional specifications. For dimensional tolerances on your part, again, you can refer to the North American Die Casting Association Product Specification Standard, which will tell you a lot of tolerances to use for a variety of dimensions for your die casting. In addition to that, you need to be considering how you're going to draw your datum scheme on your die cast part. Be careful with the types of features you choose for your datums. You want to choose as repeatable of features as possible. If your part has any machining that goes into it, those are great candidates for datum features. And you want to avoid choosing datum features for little small parts that are going to be hard to measure or very, very big features that are going to have a little bit of distortion which could throw off the dimensional values. And if possible, you want to dimension a feature from datums which are formed in the same side of the mold. And the reason is there's always a little bit of variance between features that are formed by different sections of the mold. So that variance can cause issues with your dimensioning scheme if the datum is on one side of the part and the feature you're checking is on the other. And another thing to consider is, as the other guys have said, your die-cast part is going to have some draft and radii throughout. So you need to consider that when dimensioning the different features. If you're dimensioning to a vertical wall, how high up that wall do you want to actually check? Because the value of that wall is going to change the further up the wall you go. So trying to identify whether you're checking at the top of the wall or the bottom of the wall, that can help out. In addition, if you're wanting to check to a feature that has a radius on it, do you want to check to a theoretical sharp corner or the top of the radius? These are all just things to think about. So in addition, try to include as much detail on cosmetic and functional specifications as you can. try to quantify as much as you can within reason. Too little detail leads to ambiguity on the part, which can cause issues down the road, and too much detail, if it's unnecessary, can just increase the overall cost for inspection if it's a very cosmetic part. Some things to consider adding quantified specifications for on your blueprint would be marks for where the ejector pins actually push the part off of the mold will leave a little indentation on the casting. So how deep can that indentation be, or how raised can that indentation be? And anywhere where two molding components come together may leave a little thin section of metal called flash. If that were to be on the end product, how big can that flash be? How thick can it be? Stuff like that is important to include. And if there is a specification needed to control how much a gate vestige can be left on the part after the gates and overflows and runners are all trimmed away, those are all things to include as well. Some other specifications that you may need to consider if there's a porosity requirement, whether that be external or internal. For example, a way to control the external porosity is maybe you say the max surface porosity on your casting should be no bigger than 0.5 millimeter in diameter or something like that. Or if there's an internal porosity requirement, perhaps your part needs to be x-rayed or leak tested. And if that's the case, try to avoid saying something like the part can't leak, because that can be somewhat vague, because there will always be a little bit of leak path in some way during the testing process. So try to identify what leak rate is acceptable under what pressure, and try, if it needs to be x-rayed, what x-ray spec is important. And as Rob mentioned earlier in the presentation, as the tool will age, different defects may show up, stuff like heat check. And if there's a critical area of your casting that may be prone to heat check, that may cause problems as the tool ages. So try to identify the critical areas as much as possible. So now we're going to transition into a section to talk about how to convert a die casting from other processes, and just talking about the advantages and disadvantages in doing so. And John alluded to a lot of these things already, but just to reiterate, die casting processes in general have a huge cost savings on a piece part price basis, even though the upfront tooling costs may be more, and die casting is in general a very good candidate for nearly net shaped parts with tight tolerances, good cosmetic finish, and higher structural integrity, and as we said before, pretty efficient material utilization, so you don't have to pay for a lot of wasted material. So now back to John.
Thanks, Neil.
Before we kind of wrap up and move on to the next section, we do want to reiterate we're going to go through the conversion to the other processes. As we go through some of these processes, if you recognize one where you make products with that process, but you are interested in converting to a die casting, all the stuff that we just talked about, the engineering team and the sales team at Chicago White Metal are committed to making that conversion happen and making it be economically viable for you guys. So if a lot of this information was too dense or you didn't catch everything, that's fine. We don't need you to be experts in die casting. That's what we're here for. But we do need the opportunity to help you make this more economically viable product, and we're ready when you are.
Thanks, Rob. So I know we're about 15 minutes away from the top of the hour, and we're not going to be able to go into the details of every one of these processes, but as we've been indicating, die casting competes with a wide variety of processes, and sometimes your application is an ideal fit for die casting, sometimes it's not. So in lieu of the fact that we'll be time constrained, I'm only going to briefly touch on some of these different processes and give you a little better feel for maybe in a snapshot view why die casting may or may not be a good fit as it compares to these. But I also want to tell you that every one of these processes are covered in more detail in additional webinars and resources that are available for download and viewing on our Die Cast Design Center. So please hold to the end, and we'll give you details about how you can register on that site, and these can be available to you. But yeah, just to get started, let's talk stamping. Stamping, something I'm sure everybody's familiar with. And just in a real general sense, die casting does not compete with stamping if you're really talking about a very simple 2D design, you know, that it can easily be made at one thickness and so on. That's ideal for stamping, and it doesn't give die casting much of an advantage. So in general, die casting competes with stamping when the stamping gets more complex, and the stamping then has a lot of bends and complexity. The more it becomes a 3D design versus a 2D design, the more likely die casting should be something to be considered. So, you know, in both processes, there's an upfront tooling investment, and sometimes with stamping, that investment can be very, very high, especially if there's multiple dies involved. I'll skip this detail and move on to another process because, again, this is kind of a cursory review. Extrusion. So, again, extruding is really 2D, but it's extended on one length into a 3D process. And if the shape is adequate for your needs, then it's pretty hard to beat an extrusion process. But if your raw extrusion needs to be then machined or additional processes added to it to get all the geometry required, then it might be more appropriate to look at die casting as a way to go. So both, again, have tooling cost up front, but extrusion generally a lot less. But it really comes down to, can extrusion give you the complete part you need? If you're talking about multiple extrusions that are attached or extrusions that are connected to stamping, sometimes all that can be combined into one three-dimensional die casting. Machining. Now, machining can mean a lot of things. Without even really talking about this slide, just machining in general. Low volume parts are often machined. You can quickly change geometries and so on, and we often find that that's a precursor to a die casting as the volume were to increase. And so we're quite adept at converting what are machined products into die castings when it makes sense to do so. But this particular slide really concerns automatic screw machining, because this presentation, it's hard to cover every type of die casting, but one we really haven't covered in much detail is miniature die casting. There are very high-speed small die casting machines that are made to cast zinc, and it casted very, very efficiently, such that it can compete for small parts that otherwise would be screw machine parts. So that's really what this slide is about. So oftentimes, if you're looking at a screw machine, it could be done as a miniature zinc die casting, where those castings are produced in seconds. You know, there's cycles of 200, 300 an hour possible in the die casting process, and lower tooling cost. There's a picture of a bit of the miniature zinc die casting machine there, and another reason why miniature zinc is a less costly investment is that the machine comes equipped with a lot of moving features already built into it, and so the die components are really just attached to the end pieces of what's already included in the machine, and so the tooling cost can be lower than what it would be with conventional die casting. And there's an example pictures up on the right that shows miniature die casting, again, does very well with small parts, so it competes with screw machining, but it can also do geometries that would not be at all appropriate to be done with screw machining, as you can see from the pictures on the right. But it is essentially for zinc. If it works to do small parts in zinc, miniature zinc is definitely the way to go. Sand casting, a very good choice for low volume applications without a lot of detailed features, because die casting can cast thinner walls than sand and much more complex shapes, and so that's why it generally breaks down. You use sand casting, maybe add some machining to it if the volume is low, and you move the die casting as the volume increases. The typical die casting part on the right, it shows the complexity, including cast-in threads on the OD, which are possible to do with die casting. Permanent mold casting, just another process typically made for smaller components, can be done in ferrous alloys, whereas die casting is for non-ferrous alloys. So if it's simple shapes, permanent mold can be the way to go, but as the complexity increases and you're talking about non-ferrous alloys, die casting makes more sense. And again, upper right-hand corner sort of shows the complexity with the ribs, the bosses, the holes, all can be done net-shaped in a die casting environment. Investment casting or lost wax casting is another competing casting process. Does a pretty good job of creating surface finishes that are almost as good as high pressure die casting. Can do some net shapes. Its advantage is it can do undercuts and things like that because the cast or the mold is removed and it's not made of hardened steel like die casting. So there's an advantage there if you have undercuts or hollow shapes and so on. But again, lower investment but higher piece price. Their cycle times are longer. There's certainly advantages when the volume increases to go with high pressure die casting. Powdered metal, press or sinter is sometimes what it's called, can be a choice for small shapes, and when it's ferrous alloys particularly, so that can be the choice. Metal injection molded is another competing process, but again, typically for small parts, ferrous alloys. Oftentimes, though, we can compete using the miniature zinc die casting process. Thixomolding, it's a process reserved for magnesium and essentially can make very much the same kind of shapes that we can cast in magnesium using either hot or cold chamber technology. Chicago White Metal employs the hot chamber technology. So you'll find Thixomolding can sometimes produce slightly better properties. In those parts can sometimes be heat treatable, but on the other hand, material cost is higher, and licensing options and very limited supply of Thixomolding can sometimes drive higher prices or just constrain you a little bit more in terms of finding a good fit for your product. With that, I'm going to kind of wrap up just because of the time constraints. As I said, you can reach our website. How you would do that would be to log in and look for the links that would go to our Diecast Design Center. You can directly browse to it using that link that's shown there. You'll find a number of resources, and we're going to make some of those resources available immediately following the webinar, just as a token of appreciation for participating with us today. But we hope that you come back and visit us and pull more resources. And then also, as Rob said, we're a company that prides itself on our ability to work with conversions. Our engineers are well equipped to help you with your designs. And we're also very unique in that we cast all three families of alloys so that we have a wide variety of offerings and a full complement of additional services so that all the finishing and so on can be done to your die castings here at Chicago White Metal Casting. So with that, let the questions continue. Mike Dimitrov is still busy answering questions, but on behalf of all of us here as part of the presentation team, we thank you for your participation. We hope that you participate in the future. We'll continue with the webinar series, and we look forward to working with you on some exciting projects down the line. Thank you.